got a phone call. Alright, so we were breaking down this right here. We've got our gravity and our normal, and in the y direction we also have this force P, and the P is going to the left and down, so it's pushing down like this. So I'm going to call this Px and then Py, just breaking it up. And then of course we have the friction force pointing to the right like this. So let's start with the normal force and the weight. Well, they called it weight, so we'll call the force of gravity weight. Normal force will not be equal to the weight right here, because when we add these two, that's what adds up to your normal force, because this is still balanced, because we said it was constant speed. So normal would be Py plus the weight, which means that your normal force is going to be greater than the weight alone, because it's the weight plus something else. So we can cross off B and C. But then between A and D, it says that the normal is greater, so we're choosing between these two. It's tempting to say that P would be equal to F, because you're like, ooh, balanced. But what's equal to F is actually the X component of the P force, whatever it is. Or push, yeah, I guess it's for push. Anyway, only the X component of P is equal to the force, which means that the total force P would have to be greater than the friction force, so that would be A. 16, we've got a 5 kilogram block resting on a horizontal surface. The coefficient of static friction is 0.5, coefficient of kinetic friction is 0.35, and we have a force of 260 newtons applied as shown. So this is 260 newtons, and we want to know, oh sorry, I didn't put a question here, what is happening then? So let's think about it. If it starts from rest and you apply a force, well, before it moves, you have to overcome the static friction force. So let's find what the force of static friction is. Static friction, that would be mu Fn, the maximum. Of course, we have, let me just redraw this. So the force of gravity would be 500, because mass times 10. That means my normal force would be 500. And then, of course, the applied force of 260. So coefficient of static friction, 0.5 times normal force, 500. That's going to give me a static friction force. The most static friction could be is 250 newtons. So then this would be 250 newtons like this. Right? So the applied force does overcome the static friction, which means it will start moving. And it's more than the static friction force, which is definitely more than the kinetic friction. If you weren't sure about the kinetic, well, then let's check. So kinetic friction is still mu Fn, but now I have a new mu, same normal force. So this would be, what's it, 175 newtons. So either way, you have an applied force of 260 and you have a friction force. Once you overcome the static, then it would switch to the kinetic, which would be 170. Either way, you definitely have a net force to the right, which means you have an acceleration to the right. So your answer was it accelerates to the right. It does not remain at rest because you overcome the static friction with this applied force 260. It does not move at constant velocity because you would have to have 260 opposing it to move at constant velocity. It definitely moves before 490. It moves for over 250, which is why the 260 made it move. And we can draw conclusions. Number 17, we've got a 1,000 kilogram car initially traveling at 30 meters per second. They apply the brakes. The braking force is 9,000, and it deaccelerates to a stop uniformly, meaning like constant acceleration. How far does the car travel? So I'm going to say I'm looking for like delta x of the displacement. You could call it d if you wanted. This is my mass. This is my initial velocity, v naught. This is the like net force or the average force that's applied. It doesn't say anything any other force, so I'm going to assume that's like a net force. And then it goes to a stop, so v is 0. Just having mass in net force, I can find my acceleration because acceleration is net force over mass. So this gives me an acceleration of 9, and then because I know v naught is 30, v is 0, acceleration is 9, and I'm looking for delta x. Now I just look at my kinematic equations that would help me find displacement. The first two have time, which I don't have and I don't need, so that brings me to the third one, the v squared equals v naught squared plus 2a delta x. So 0 squared equals 30 squared plus 2, 9 delta x. Now, some of you might saw this and be like, wait, but I get a negative displacement. That doesn't make sense. No, it doesn't. This acceleration would technically be negative because it is a stopping force. That means automatically your force is opposite to the direction it was moving. And it did say deaccelerates. It just didn't tell me that this is a negative force because it's not giving me like directions here. It's saying it's a braking force, which means against the motion. So if this is positive, this would be negative. Which is how I get the 900 minus 18 delta x equals 0. So I subtract that over and divide by 15, and that gives me 50. Yeah. Number 18, a 10 kilogram box is shown sliding to the right, a horizontal force. So this is like my applied force right here of 10 newtons. And then there's a coefficient of kinetic friction right here. So this is kinetic friction. So I can find the force of kinetic friction pretty easily because my force of gravity is 10 times 10, 100, and then my normal is 100 because it's balanced up and down. My coefficient of friction, 0.2, it's already moving, so I don't have to worry about static friction. I don't have to worry about it being less or overcoming. It's just mu of n. So that gives me force of friction is 20 newtons. Well, if my force of friction is 20 newtons and my applied force is only 10, that means that my net force is actually to the left. So if my net force is to the left, that means my acceleration is to the left. Now it told me the velocity is to the right. So if I have a velocity to the right and acceleration to the left, that means it's slowing down. So I for sure have an acceleration to the left because you have a net force to the left. And it is in decreasing velocity because your acceleration is opposite to the way it's moving right now. Number 19, consider the stack of 3 blocks on a table as shown. Which of the following is a valid ranking of some of the contact forces between the blocks in the table? So pretty similar to the big one on the elevator earlier. So let's just think about what ones have to be equal to each other. So between 3 and 2, that's the same as 2 and 3. 2 on 1 is the same as 1 on 2, and then the table on 1 is the same as 1 on the table, because that's Newton's laws. They have to be equal to each other. So here, I can cross off A immediately, because the block 1 on block 2 is equal to block 2 on block 1. Not, like, this one is definitely not greater than this one. They have to be equal to each other. Here, so I totally agree with this part. The table on block 1 and block 1 on the table for sure are equal. What I disagree with is block 2 on 1, so the force between these two is equal to the force between these two. That's definitely not true, because if these are at rest, then this one right here is holding up, so like the table is pushing up the weight of all of these, whereas block 1 pushing up on block 2 is only pushing up the weight of these two boxes right here. So I disagree with B. Let's look at C. So none of these should obviously be equal to each other because they're matching pairs, so that checks out. It says that block 1 in the table, the force between these two is greater than the force between these two, which is greater than the force between these two, and that makes sense because this one is holding up 6m, this one is holding up 3m, and then this force is only holding up 2m. So I agree with C. And then again, D is not all equal for the same reason that B were not all equal to each other. We've got a crate of mass 100. It's at rest on a not a frictionless, didn't say that, a horizontal floor. So I've got a force of gravity 10 times the mass, which is 1,000, and we have a normal force of 1,000 because it doesn't say anything about another force like up or down. The coefficient of static friction is 0.4 and coefficient of kinetic is 0.3. We've got a force of magnitude 344 applied to the crate parallel to the floor. So let's say that's up to the right. It could be to the left, it doesn't matter. So 344, and I want to know what happens. So let's first of all, if it's starting at rest and I have an applied force of 344, I need to overcome the friction, the static friction, because it started from rest. So let's find what the most static friction could be. That's mu of n. I'm going to use coefficient of static friction, which is 0.4, times normal force, which is 1,000. So that's going to give me 400 newtons. So the most the static friction force could be is 400 newtons. So this is not enough to overcome all the static friction that could happen, so it will not move. Now it's tempting for a lot of people to be like, oh sweet, so then I have 400 this way, so that's a net force of whatever, that's subtracted 56. But that is not true right here, because static friction is actually less than or equal to the mu Fn. So if something has a maximum static friction force of 400, if I push it at 300, it's not pushing me back at 400, it's just pushing up to 300. It's, again, like less than or equal to. If nothing is pushing on this box at all, then it has zero friction force. So we have to be really, really careful with static friction. That's not necessarily an equal sign. It could be a less than or equal to up until the point where it starts moving. Masses 1 and 3 hang freely, and M2 sits on a frictionless table. When M3 accelerates down, this one accelerates to the right, and this one accelerates up, so they're like accelerating this way. If the mass of M3 was increased, what would happen to the acceleration? Would it be more or less or the same? So if you increase this mass right here, now you have a greater force pulling down all the masses in the system, so you would have more acceleration because you have a greater net force on the whole system. If you were to increase mass 2, what would happen to the acceleration? So this is actually going to make it less of an acceleration, because here you're still pulling down as much here and pulling down on this side. So you actually still have the same net force on the system, but now you have it over a greater mass. So your acceleration of the system is the net force on the system over the mass of the system. If you increase this, you just increase the mass of the system, but you didn't help by increasing any of the forces. So you're going to get a smaller system acceleration. And then 23, if you were to increase mass m, what would the new acceleration be? So if you just increase it a little bit, not to where it is more than the other mass, then you're actually going to decrease the acceleration, because right now this one is greater and it's accelerating this way because this has a greater mass. Here, this has a mass that is obviously keeping this from just accelerating at gravity because they're all connected. So if I increase this, then I'm going against that force. I'm making a smaller net force on the system up until the point when then it becomes the same mass, and then they're balanced, and then if this becomes even bigger, then I'll start to accelerate the other way. But I was just thinking increase before it starts accelerating the other way, so that would be a smaller acceleration.